Hi everyone. Today we're excited to have Dr. Christine Gabrielse, a research scientist at the Aerospace Corporation. She previously completed a PhD at the University of California and is an expert on magnetosphere-ionosphere coupling and Aurora science using both space and ground-based data. So today she'll be speaking to us about her work on energy transfer via the Aurora on mesoscales. And yeah, we're ready when you are. Thanks, Christine.
All right, thank you so much, Emma, and thank you all for inviting me and coming to listen to what I have to share today. Apologize in advance, I'm getting over a cold, so if I have to cough or clear my throat often, I'm sorry about that. So let's get into it though. Emma told me that, I can advance my slide. There we go. Emma mentioned to me that a lot in the audience are grad students and that while most are studying physics of some sort, not everybody has a space physics background. So I want to draw you all in with these beautiful pictures of the aurora so that you don't think that space physics is boring. It's actually very fun and, as you can see, very beautiful. I hope you all have the chance to see the aurora at least once in your lifetime. I did have the chance many moons ago to see the aurora in person, and it's definitely something that just you can't describe in words. You can't compete. It's gorgeous. So we established the aurora is gorgeous. It's beautiful. Yeah, but why is it important? Why do we care about it? Well, first of all, we look at the aurora as part of energy transfer process. So the aurora is heating the atmosphere, and it causes the atmosphere to rise. And when the atmosphere rises, it can actually increase drag on satellites and the International Space Station. So here on the right is this plot that is showing the space station altitude over time. And it's just following the predicted trajectory until suddenly there was a geomagnetic storm, which caused this dazzling display of aurora. But when that happened, you see the ISS suddenly drop in altitude somewhat unexpectedly. And that's because the upper atmosphere rose and put drag on the orbit. And so if measures aren't put into place, satellites can actually, and have actually, fallen out of the sky due to this. The aurora can also affect radio propagation, and it also has other effects in the atmosphere, such that atmospheric physicists care about for modeling, such as neutral winds. And actually, let me also just quick mention for our non-space physicists that you can see the aurora as having these lines here. That's because particles are following Earth's magnetic field and depositing into the upper atmosphere. So these vertical lines are actually us being able to see those invisible magnetic field lines, which we'll see more in a cartoon movie here. So this is to kind of show what kind of events are occurring in space that can create that beautiful display of aurora. So as you may know, the sun is constantly spewing energy towards the Earth, sometimes via explosive storm events and sometimes just this constant barrage of particles, which can cause smaller substorm events. And so Earth's magnetic field acts as a shield to block much of the sun's radiation, but some of that energy can sneak into the system via reconnection when Earth's magnetic field lines come together. So let's back this up. That's this right here, reconnection on Earth's day side. And so the solar wind and the sun's magnetic field is pulling back Earth's magnetic field into the tail. And so we have reconnection in the tail, which allowed that energy from the sun into the system. And when that energy is explosively released in released in the tail like that, it is flung towards the Earth. And some of that energy follows along the magnetic field lines and is deposited into Earth's upper atmosphere, which creates this auroral display. So one reason the aurora is interesting to study for someone who is a magnetosphere scientist like myself is that it is an indicator of those magnetotail processes that are going on. So as you can see, the magnetic field lines out here are attached to Earth's upper atmosphere in the northern and southern hemisphere, and that's when the aurora occur. So here's a snapshot in time of that movie we just saw, where after you have that tail reconnection, you have these mesoscale plasma flows shooting towards Earth, carrying all this energy, which create what we call field-aligned currents that run along those magnetic field lines. And those field-aligned currents accelerate the particles that are here, and those create these mesoscale auroral forms called streamers. And so here's what that looks like if you were to be sitting on the ground outside in Canada. You will see this bright, narrow auroral form moving from north to south. And that's essentially a way to watch this streamer, which is moving from the tail towards the Earth, which then maps as this travels from north to south in the aurora. And that has other effects in the atmosphere as well. These colorful plots here are superdarn radar, which shows in red color plasma flows in the ionosphere that are traveling equatorward. And so you can see that along with the auroral structure, you also have the atmosphere itself moving along with it. And so that creates a lot of flows and vortices and electric fields in the atmosphere. So that's just one more reason why this is important to study. This is an example that I wish I could show the images from this paper called The Development of the Auroral Substorm by Akasofu. I encourage you to look them up if you haven't seen them. I'm not allowed to show them because they're behind a paywall, and my company has very strict copyright policies. But what Akasofu did is he sat outside in Alaska staring up at the night sky night after night and recorded what this movie I'm about to show you, this auroral substorm looked like. And he found that every substorm had a very similar pattern, so that he was actually able to sketch them. So if you look up this paper, you will see hand-drawn sketches of the aurora. So this is sped up in time, but this is what the auroral substorm looks like from the ground, where what I'm using are called all-sky imagers, which are 360-degree field of view cameras that are on the ground looking straight up into the night sky. And here they've just been stitched together and plotted on top of North America to show where the aurora is occurring. So let's play that again just because it's beautiful. You see that explosive activation in the aurora basically moving poleward and surging westward. And you see a lot of these very narrow, what we call mesoscale structures in the aurora forming. And so you'll see from this talk that those are actually quite important. But before we get to that, one other reason the aurora is important to study is conductance in the ionosphere. So particle precipitation, or the aurora, increases conductance in the ionosphere, which is that upper atmosphere that has charged particles. There's a positive feedback mechanism via Ohm's law, where you have current is equal to conductance times the electric field, whereby you have increased ionization and conductance from precipitation, which meaning the aurora. And if the conductance increases, then you also have increase in field line currents, which, as I mentioned, if you recall from my earlier slide, field line currents are what accelerate those particles into the upper atmosphere. And so that causes even more precipitation. And so it's this positive feedback mechanism. And conductance affects currents and where they close, Joule heating and energy transfer, feedback loop with the magnetosphere. In addition to what I was just talking about, other papers have shown that in the long term, the background conductance can influence the large-scale convection and therefore the magnetotail pressure distribution, which may change the large-scale dynamics and the mesoscales that comprise them. That's a lot of jargon if you're not in space physics, but I did want to share that for those students who are in the space physics field. Also, increased conductance decreases the electric field, again looking at Ohm's law, which slows the plasma flow speed in the ionosphere. So you can see that there is just a lot of feedback and relationships, all that has to do with particle precipitation and the aurora, and how that affects both the magnetosphere, where we think of it as it being the source of that aurora, and also the ionosphere and upper atmosphere, where a magnetosphericist sees that energy being deposited. And sometimes we see that as the final ending place to the energy transfer that we care about. But that's just the start for atmospheric physicists, where that's part of the input of the energy into the system that they're studying. And so it's sort of like we're taking our end and giving that to them, and then they go off and solve lots of cool problems in the atmosphere. But then, of course, as this slide pointed out, the magnetosphericists can't just ignore that it's not really just the final resting place of all the energy transfer that we're studying. It's also having feedback on the magnetosphere itself. So the motivation of the work that I've been doing is to understand the aurora's finer structure. As I pointed out in that movie, there's a lot of very narrow streamers and auroral features, but until now, for the most part, current models are capturing what we call the global aurora, but not these finer structures on mesoscales, which in the ionosphere we're defining as less than 500 kilometers wide. And those can relate to what we call mesoscale flows in the magnetosphere, which for our magnetosphere physicists, that's generally a few RE wide, like these bursty bulk flows we see after reconnection. And so here's an example of one of the auroral models that we use called Ovation Prime 2013. And it predicts the aurora using the solar wind inputs, like how fast is the solar wind blowing and what's the density, the ram pressure, all of these things can predict this kind of global outline of where the aurora is occurring. But as you can see, this is, well, very global, and it's missing all of those mesoscale finer structures that we saw in the earlier movie. Here's another example where a state-of-the-art models are trying to model the conductance as in the ionosphere, which we just mentioned is very important to know and constrain. And so as you can see, this is during a storm and a geomagnetic storm. And the black lines up here are the data points. So they represent the truth as observed by Pfizer. And the different colors are different variations of the RCME model modeling the conductance. And so you can see that when there was diffuse aurora, which means the more gentle, not very dynamic, not super bright, can be bright, but it's not really full of those dynamic narrow features. You have a very good match between the model and the data. But when we look at the more discrete aurora, which are those mesoscale features that are very dynamic and they're caused by those, field-of-line currents that we just talked about, the models don't do so well because the models don't include those physics. And so we're missing what is the conductance due to these mesoscale aurora. So we want to better constrain, better characterize what is the inputs from these mesoscale dynamic aurora. So that's our motivation, to understand the aurora's finer structure. We want to know what scale sizes are important, what are the characteristics of the auroral precipitation, like the energy flux and the energy and the conductance, in order to understand the energy flow in the system. And so there are multiple data sets available to study the aurora, and I'm going to explain how some of them, they have pros, but they also have cons. So there are difficulties answering this question that we're interested in. And one is that meridian scanning photometers, which I have shown the field of view here in green, plotted on top of an all-sky imager. They provide the different colors of the aurora, so like red, green, and blue. And from that, you can extract things like the energy flux and the energy of the population. But as you can see, it's only monitoring along a single line of longitude. So you have no idea what's going on over here or over here or over here. You only know what's going along this line of longitude. And then incoherent scatter radar, such as Pfizer, allows us to calculate accurate conductance, but only at a single point in space, like this right here, where I've plotted the Pfizer location on top of an all-sky imager. So again, it's great for maybe like statistical studies where you can get a more global picture by calculating the conductance over many, many, many events. But if you want that like specific event or to really characterize these finer structures of the aurora, it's not the best. And then the ASI itself is kind of getting there. It allows you to see the different scale sizes and over 2D. And so some studies, as I've listed here, have utilized an all-sky imager to address these questions. But as you can see, it's still spatially limited because it's only covering, this much of the aurora, whereas in the movie I just showed, you saw the whole substorm expands over all Canada almost. And then finally, satellite overpasses like DMSP, they provide the exact energy flux and energy of the particle population. So again, they're great if you want the precise numbers. They're great for statistical studies again, and they have been used statistically to build up a database. But again, a satellite overpass means you only have the data while the satellite is flying over your location, but once the satellite is gone, you can't monitor what the aurora is doing anymore. So a substorm, which lasts for 90 minutes, you can't watch that whole thing with a satellite, unfortunately. So that's why for our study, we decided to use this mosaic of all-sky imagers, which were built by the NASA THEMIS mission, as they provide a 3-second cadence over hours of time over this large continental scale of the aurora. And so this is just an example of that same substorm now converted into energy flux, which I'll be explaining how we did in the rest of this talk. Of course, while I sing the all-sky imagers praises, I also want to admit, of course, there are limitations, such as each individual all-sky imager is usable about 50% of the time, with multiple cameras at the same time, about 20% available due to cloud coverage. If there's clouds, you cannot see the aurora when you're viewing from the ground. Also, at very low elevation angles, obviously the camera is located here in the center of the field of view. So when it's observing the light at low elevation angles, it's cutting through multiple flux tubes. And so there's kind of a mapping issue. The white light all-sky imagers so THEMIS just provides like how many counts of light is there, which is just considered white light. So that's not sensitive to detect the really, really, really dim aurora that shows up as red in the night sky. And then finally, our methods, which I'm about to describe, does assume a relationship between white light intensity and color intensity, which translates to a relationship with energy and energy flux, which has been shown in previous papers to be true for discrete aurora. So that's a valid assumption. It's not as good for diffuse, but we will be showing later in the talk it wasn't as bad as we thought it would be either. So how do we get, as I mentioned, energy flux, which is the interesting parameter, from just white light counts from all sky imagers? Because from energy flux, we understand how much energy is being transported and deposited in the ionosphere, and from that we can also get the conductance. So because precipitating particles of increasing energy penetrate deeper into the atmosphere, the aurora's color, which changes with altitude, is indicative of the particle energy and energy flux. So for our non-space physicist audience, if you can think about the atmosphere, it's very natural to understand that at the highest altitudes, it's not very dense at all because we're getting close to outer space. But the lower altitudes we get to, it gets more and more dense. And there's more and more molecules in the atmosphere. And so that means if a particle is coming from the magnetosphere and it does not have that much energy, it moves pretty slowly, and it's more likely to hit an atmospheric particle pretty high in altitude. And so these less energetic particles hit the atmospheric particles up here, and those atmospheric particles, which are oxygen, release a red color. So when you see the red aurora, that means you have a very not energetic population raining down. Now, a more energetic particle coming from the magnetosphere is going faster, so it can make it past a lot of the, through this not very dense region before it runs into a particle in the more dense region of the atmosphere. So making it to a lower altitude, it now strikes oxygen molecules that release a green color. And the most energetic ones make it even farther down, and then they strike these nitrogen molecules, which release a purplish bluish color at the lowest altitudes possible. And so if you can measure the ratio of how many blue to how many green to how many red, you can actually determine what is the energy flux and the average energy of this population that's raining down. And so we do that using an energy flux lookup table that was built using the B3C Auroral electron transport code. So that's an atmospheric model that uses physics that I did not build. This was built in the 70s and then upgraded in the 90s and later, where it actually can calculate based on these ratios what should be the energy flux and mean energy of the population. And so we can create, I'm not going to read all this, don't worry, but you can create these lookup tables where if you know the ratio of, say, red to blue and green to blue, you can then look up and say, aha, then I know my mean energy of the population was, say, 1 keV. And then also you can get the energy flux from that as well. Okay, so, but Christine, you're thinking, you just told me you're using white light imagers, so how are you going to utilize this color ratio methodology you just described? Well, the way we do that is we compared the white light counts with data from the meridian scanning photometer, which, as I mentioned before, does provide the brightness in the green and blue and red wavelengths. And so this is what meridian scanning photometer data looks like, where the y-axis is the latitude, because as I mentioned before, the data is along a single line of longitude over time. So the x-axis is time. And so what you see, this is called a keogram, is that you have a brightening here that then moves poleward. because over time, if something moves up in the y-axis, that means the aurora is moving poleward in time, or equatorward if it's moving down the y-axis. And so what we did is we just created these scatter plots, actually, of the THEMIS white light on the x-axis here versus the green light intensity from the meridian scanning photometer on the y-axis. And you can see that it does follow a generally linear function in log-log space, where the solid yellow line is the median, and the dashed lines was the quartiles, and then the solid green line is a fit that we made to the data. And then we related the green color to the blue and the red. So we used just the meridian scanning for the MSP data itself, where we plot green versus blue. And you can see it's a very clear, very tight linear relationship between the green and the blue data. And then we also did a relationship between the green and the red, which, not surprisingly, there's not as good of a function that relates the two, but there is somewhat of one, which we fit here with this red line. And so that way, by having the white counts, we can convert to green, blue, and red. So this is to show you how well that did, where here I'm plotting the MSP data, which we're taking as truth, to the all-sky imager, which is the converted white lights to green. So here we have the green comparison and the blue comparison, the red comparison. And then using those lookup tables, we converted both data sets to energy flux. So here's the comparison for energy flux and average energy. Where here then I have also provided the ratio. So here is the ASI divided by MSP data for the energy flux, where green means 1, so green is a good match, and blue means, we're underestimating, and red means we're overestimating. So that's for the energy flux and the energy, and this is just subtracting the two. But I also determine the percent differences. So the percent difference, the median percent difference is around 40% for most parameters, with quartiles near 20% and 70%. All parameters, meaning if I took the percent difference between energy flux, mean energy, or the different colors, and those are all laid out here in this table, which if you're the type that wants to look at it closely, you can also look at our published paper. But you can see the median, just quickly looking, is around 40% for all these parameters. Whereas the mean was around 50% with standard deviations near 40%. And so we were actually pretty pleased with this, given the assumptions that we had to make. We also compared ratios and differences. So this is basically what was plotted here, where we see that the ratio is usually near 1. For example, here's the mean ratios here are near 1. You can see plus or minus 0.9 standard deviation. So again, just kind of indicating it's a fairly good match for what could be seen as kind of a cruder methodology. So this is an example of our new data product, where we can now plot energy flux and average energy in 2 dimensions over time. So here are just some snapshots of the substorm as it's evolving and the energy flux from it. Here's that movie. I guess we've already seen it, so we'll just let it go for a little bit because it's pretty, but it's also a little slow. So there's the start of the substorm. Here's it expanding poleward. You see all that finer structure in here. And then we eventually also see it progressing westward. And so, what I just described to you sounds kind of fast and simple, but a lot of working with the data was put into this, like subtracting out background street lights and stuff like that. That was sneaking in there. See, okay. So then getting to some scientific results, we wanted to look at, what is the mesoscale contribution to the substorm energy flux and average energy? Because a lot of us have been saying we think these mesoscales, these smaller scales are important, but unless you quantify that, you don't know if it really is important. And maybe we're just, chasing shadows, and really we'd be fine just looking at the global models of the aurora. So we did that, we checked that by plotting here. Let me walk you through this. This is the SML index, which just indicates the substorm is happening. Here we have plotted the energy flux and at 2 different stations in that kilogram format. So this is the latitude versus time. And now we've plotted down here the total energy flux that we calculated from the all-sky imagers, which is in black. And then the different colors, red, green, and blue, are looking at the smaller scale sizes. So all of the energy flux that was contributed under 500 kilometer scale sizes are in red, 300 in green, and 100 in blue. And then we just divide that by the total to get the total percentage. And you can see that during the substorm expansion phase, so when that explosive auroral expansion occurred, the mesoscales contributed up to 80% of the total energy flux. And the smaller scales that were less than 100 kilometers even still contributed over 30%. And so that's very indicative of the importance of these mesoscales. And then as the substorm progressed after the expansion phase, the mesoscales do still play a vital role, as you can see, up to like 50%, 40 to 50% throughout the rest of the substorm lifetime. A second substorm was triggered here. That's what this one is here. And so for the second substorm, we also see contributions up to 60% for those less than 500 kilometers scale size auroral features. So again, just really stressing the importance of characterizing and modeling and observing these mesoscale features in the entire energy transfer process. So I mentioned that you can calculate conductance from the energy flux and mean energy. So we did that again using that B3C auroral transport code, because it again provides lookup tables relating those values to conductance. And so we, for those of you who are maybe more familiar with this area of study, those discrete aurora that are caused by field-aligned currents and are more dynamic, we use the Gaussian distribution function, whereas the diffuse aurora, which was the more quiet aurora caused by wave particle scattering in the magnetosphere, we use Maxwellian distributions. And so we have plotted those here, where the top plot is just a kilogram of the all-sky imager aurora over time. So here's where you can see you have this substorm occurring. And then below we plotted the Gaussian conductance determination. And here below that is the Maxwellian. So we're plotting the Hall conductance, and we compare the models with data. So the black is the data from Pfizer, and so that we take as truth. The blue is using the energy flux and energy inputs into the Robinson formulae, which have been used by many in the community as a quick way to analytically calculate the conductance. And then we use the B3C lookup codes in red to calculate the Hall conductance. And so you can see during the discrete aurora and even the diffuse, the B3C code version does a very good job at matching the conductance that Pfizer gives us. Where here's the discrete aurora, and here's the diffuse, and you can see that the red and the black lie almost on top of each other, whereas the Robinson formula version overestimates the discrete Aurora conductance and underestimates the diffuse. And so here we have done another comparison in a table format for differences and ratios and the percent differences. And so you can see the standard deviation or the median percent difference for the discrete Aurora conductance was only 24%, and the median for the diffuse Aurora was only 18% for using the B3C version. So again, that's pretty good, we think. And then here is just plotting the conductance in 2D. So it's showing you, if there are any modelers in the room, what we can provide is basically a grid of constant latitude and longitude points that we then provide the value of the conductance or the energy flux or the energy to, which then can be inserted into an ionosphere model, which is exactly what our collaborator has done. This image is, here we go, sorry, I was trying to find the citation, by Cheng Sheng et al., who is at UTA and is currently submitted to Space Weather, and it's under review. So this just shows an example of, here's that empirical model where you have just the global aurora without mesoscale contributions. And then taking our ASI data, he put it on top of that global model to capture those mesoscales. He's done some smoothing, and then he shows the difference by subtracting the merged from the smoothed, where the top is the precipitation inputs, and then the bottom is, by using those inputs, he calculates the height integrated Joule heating using his model, which is GITM, driven by these particle precipitation patterns. Kind of takeaway from his paper under review is that mesoscale precipitation forcing is found to enhance ionospheric and thermospheric disturbances with rich structures and magnitudes of a few tens of meters per second in the horizontal neutral winds at 270 kilometers and a few percent in the neutral density at 400 kilometers. So in less jargon words, it's basically saying that these are important to neutral winds and densities in the atmosphere. These ASI inputs are also being used to determine heat flux for the first time. So knowledge of electron heat fluxes is especially important in the high latitude auroral region, where the magnetic field lines connect the ionosphere with the very large energy reservoir, which is Earth's plasma sheet. The electron heat flux has regional variation and strongly depends on the magnetospheric conditions that are affiliated with these magnetic storms and substorms. But the energy heat flux cannot be measured by any space plasma observations because it's carried by electrons with energy below 1 eV. And that's too low, the instrumentation kind of gets in the way. So this new methodology that was done by colleague George Kazanov at Goddard, and this is the paper if you want more details, combines the ASI data with modeling using the superthermal electron transport, or STET model, offering a novel approach to determining the heat flux, specifically on these short duration event studies that cannot rely on the long duration global events. So here, again, we're showing the inputs and the left two columns, where here's our energy flux and mean energy over time. And then George has used this as inputs to then determine the electron heat fluxes over time, which he plots here in the right column. And as you can see, that it starts out dim but kind of grows and kind of looks like it stays steady afterwards, which is what he's showing here in this plot, which is essentially if you have some input for about 5 minutes, then you reach this steady state for the heat flux. But I guess the main point of this story is just that these inputs are being able to be used in various models to answer questions that were previously unanswered. Next, we have applications for NASA's GDC mission. So this is NASA's Geospace Dynamics constellation. It's a mission concept to study the coupling between the magnetosphere and the ionosphere-thermosphere system and how that coupled system responds to external energy input. Sounds familiar, right? That's exactly what we've been looking at. So I'm on this SOFI IDS team, meaning an interdisciplinary scientist team led by Yue Deng at UTA. And she and her team are using the GITA model, driven by observations and other models, to support the refinement of the GDC constellation configuration and mission requirements. For instance, what spatial and temporal resolutions are necessary for GDC to further our science? The all-sky imagers will provide the precipitation characteristics from historical real-world events. And this is especially important to include are these mesoscale auroral features, which are not inherent to GITM. As I mentioned, so far our global models are very global in nature, and they need our observations to help inform them, to improve them, to include those mesoscales. And so it's been demonstrated to NASA there's a strong importance for ground-based all-sky imagers to provide GDC science return. And the problem is actually that THEMIS, the mosaic of all-sky imagers I used in this study, will be gone by then. So we are really trying to emphasize the importance to support future mosaics, such as the Canadian T-Rex, which is going up now, and some, or even new versions, since T-Rex will already be maybe 7 years old by the time GDC launches. So assuming that there are ASIs available when GDC launches, they can be used during the mission for validation, so you can compare when the satellite's going overhead, are we seeing the same structures? And also for supplemental and contextual information. As I mentioned before, satellite overpasses only get what you can see while they're going overhead. So a mosaic of all-sky imagers will help to provide that contextual information for GDC. So in summary, we developed this technique that's using these THEMIS all-sky imagers to determine auroral energy flux, average energy, and conductance in 2D over time. In this talk, we applied the technique to study 2 back-to-back substorms, and we demonstrated that mesoscales are very important contributors to the substorm total energy budget. Our results are being used as inputs to global atmospheric models, such as GITM, which further show the importance of mesoscale auroral precipitation on neutral densities and neutral winds. They're being used to calculate heat flux, and our techniques are being used in the GDC mission planning. For future work, I should say current work, I'm studying this famous March 17 St. Patrick's Day event, but it requires removing the moon, which is another issue you have with all-sky imagers. But it's kind of exciting. It took me way more time than I thought, but I've developed a technique that does allow me to remove the moon using various image processing techniques. And so now I'm working to show how mesoscale structures are important for this storm and provide that as inputs to people who are interested as well. And also in the future, we'd like to include this Canadian T-Rex ASI data, which, if you haven't heard, does provide the red, green, and blue colors. So then I don't need to make these assumptions using white light imagers to get those ratios. I can actually have the full 2D, full color spectrum, well, not full color spectrum, but RGB, to get the information that we're after. So that's all I had for today. Thanks again for your attention, and if you have any questions, I'd be glad to take them.
Great, thank you, Christine. Does anyone have any questions, either in the room or online? I'm not sure if we can raise our hands in Teams. If you have a question, yeah, please raise your hand. Yep. Oh, I think I can see. Yeah, Harlan, I'll go with you first.
Hi, Christine. Really great talk. Good to see you. Hope you're doing well.
Thank you.
So I have a question that is a little probably beyond the scope of your talk, but maybe connected, and that is in the subauroral region, there are there's evidence of effects of the global electric circuit from precipitation from the radiation belt that is important for Schumann resonances, which is, the surface of the Earth and ELF waves rattling around with the lower side of the ionosphere. To what extent are those connected to the auroral region through currents that might be flowing? Is there any evidence that there's a connection between those two?
So I have to admit, I do not delve much into the subauroral regions. I don't know, I probably don't have an answer for the specific items that you brought up, but I do know that several people in Yue Deng's MIRI group, like Larry Lyons, have studied how substorms, and these streamers specifically, do actually set off these TIDs and TADs, which are like traveling ionospheric disturbances or something like that, into the subauroral regions, and you can see them propagating south of the aurora. So in a generic sense, I can say that yes, these substorms, these aurora, these high latitude features are quite important to the subauroral and lower latitude regions because of how they just set off these atmospheric, I would call them like waves propagating south. Does that sort of address your question?
Yeah, fair enough. It was kind of an ill-posed question, so thank you for your swing at it.
Okay, sorry, thank you.
I can see we have another question from Slava in the chat. Oh, maybe not. Is that? Okay, no, they disappeared. Anyone else have any final questions for Christine? If not, I have a more general one that, sorry if you don't, have an answer to, but the more, because I'm not an expert in this at all, so the more global model that you showed at the beginning also had prediction of the DST index with the more that was good at the quiet times. Have there been any more recent models using, I guess, these observations on the mesoscale to also improve the DST and estimate for the non-quiet times?
So the DST, this is actual data. This is not modeled DST. So
sorry, I saw the pink and blue lines laid over top.
Yes. So these are trying to model the conductance. And so the black is the conductance. And as you mentioned, the quiet time is modeled fairly well. And it's this active time when you have the more active mesoscale structures that are not modeled as well. And so far, as far as I know, there's not something that really models this well. And so that's one reason we were motivated to try to provide these inputs using observations to help the models improve. I mean, I think that the goal for a modeler would be to eventually include the physics that would map these structures down into the ionosphere so that you could actually model the precipitation that's occurring due to the magnetosphere physics that's going on. But there's difficulty in combining models. Like you have the model of the atmosphere, you have the model of the magnetosphere, and people are trying to couple them, but it's a difficult process.
Great, thank you. And Slava has re-raised their hand, so if you'd like to go.
Now?
Yeah, we can hear you.
Oh, great. Sorry, Teams doesn't work very well on the APL network, but I managed to make it work. Actually, I'm glad that this comment, I guess it's not a question, but a comment that goes after this conversation that you guys just had, because we're obviously in CGS, we're building exactly a model like that. So I was just going to comment, and particularly looking at how you are saying you're planning to work on the March 2013 storm.
Mhm.
We've been working on that at a fairly high resolution with the entire coupled model from the magnetosphere down to the thermosphere. So we should just definitely talk more and collaborate more on this. This is an area of great interest to us and clearly to you as well.
Yeah, that sounds great. That'd be awesome.
Thank you, Christine.
Mm-hmm.
Right, if there are no final questions, I think we should thank Christine again. Thank you so much. Yeah, it's been a great talk, and thank you everyone for joining.
Thanks, everyone.
Right, see you next time.